All right, guys, so everyone here should have their Spool Racer Lab out and ready to go. Up here. Usually I would have you guys read, but I'm going to read this out loud to give you guys some information. Please either highlight or underline the key important pieces of information that you will need as I give it to you. So I'm going to read it out loud. Please follow along. This will help you in the long term when we have our reading comprehension questions. In order to move, all vehicles must overcome the forces that hold them in place, especially gravity and friction. That's very important. Vehicles can do this by generating forces of their own, pushing and or pulling against the forces that resist their motion. Most vehicles use some kind of fuel, like gasoline, to generate their power. Others may use wind or electricity. Without energy, they wouldn't be able to move. However, not just vehicles have the potential to store energy. Energy is defined as the ability to do work. Do you think definitions are important today? Yep. Underline that. Energy is defined as the ability to do work. It is the driving force behind all types of changes in the physical world. Energy makes things happen. However, energy can also be stored. Scientists call this stored energy potential energy. Is that a definition? Let's underline or highlight that. Batteries, for example, are designed to store chemical energy, which can be accessed at the flip of a switch. Somewhat surprisingly, all objects have the capacity to store energy. Probably pretty important since we're talking about what potential energy is. Potential energy can also be thought of as the energy an object contains due to its shape or position. There's another definition of potential energy that's probably important today. The act of placing a book on a shelf, for instance, increases the book's potential energy. The higher the book is placed, the more potential energy it is stored. While this energy may not be obvious, it is there willing to be released. If the book fell or the shelf collapsed, the stored energy would be converted into kinetic energy, the energy of motion. There's a definition right there of kinetic energy. And the book would fall to the floor. Okay, so we've been talking about different types of energy, and we've talked about the law of conservation of energy. When you made your graphs on your digital lesson, you noticed that the graphs went from one side and they teeter-tottered to the other. This is the law of conservation of energy. Energy is not just created out of nowhere. It transforms into something else. So that's why your graph was always 4 plus 0 equals what?
4 plus 0?
4. What's 3 plus 1? 2 plus 2. 1 plus 3. 0 plus 4. That is the law of conservation of energy. That energy is not created or destroyed. It just turns into something else. For the next part of your reading, we're going to talk about 3 types of potential energy. I would recommend that you highlight or underline those potential energies as you see them. Potential energy comes in many different forms. A book on a shelf or a rock sitting at the top of a mountain both hold gravitational potential energy due to their relative position and the force of gravity pulling them downward. Fuels store chemical potential energy and the bonds that hold their atoms together, which can be released through a chemical reaction. The rubber band that powers the spool racer uses the energy required to stretch it or to wind it up. This elastic potential energy is created by the stretchy properties and the shape of the rubber band. After stretching, when the rubber band is released, it will return to its natural state, and all of its stored energy will be converted into kinetic energy, and the spool racer will move forward. So what we're going to be doing today is we're going to be gaining potential elastic energy, and we're going to be transferring that potential energy to kinetic energy, which is going to be demonstrating by making the spool racer move. All right, right now I would like everybody to look back at the reading and write down the definition of kinetic energy and the 2 definitions we talked about for potential energy. Because this lab is about transferring potential energy to kinetic energy. Bless you.
Will we start then?
You're going to write the definition right now. They're short definitions. There's 2 potential energy definitions. There's 1 kinetic energy. All right, if you're not finished, make a big star next to these. We're going to come back to them. We're going to get on to the next part. All right, for the lab today, your priority is actually doing the lab, but there is a bunch of information that we just read. Eventually, you're going to answer the reading comprehension questions here. Okay, I don't want you doing that right now or with your lab groups. You can get this packet and reread that information and answer this during go time. You can also do this at home. What you can't do is do the lab. So I just want you to write at the top, just a reminder, okay, for reading comprehension questions, where are you going to find that answer? In the what? In the reading, yes. So it doesn't say Google the answers. It doesn't say guess the answers. It's saying use the reading comprehension questions to answer the following. So please write nice and large, use the reading. You will get points off. This grade is going to be a double grade, so it's going to be 200 points. Yes, 200 points. It's a double grade because it's a formal lab, so make sure that you're being really thorough and you're doing your best. Again, we'll come back to the reading questions at a later date. Yes.
So that means if we get like a 200 on this, our average will double by 200.
Not your whole average, but it'll be like 2 grades. All right, I'm going to come back to the actual procedures of how we do this lab in a little bit. And I'm also going to come back to the graph last. So if you guys could turn to the 3rd page under the conclusion question. So again, because this is such a big grade, you're going to be writing conclusion questions to wrap up your conclusions. When you get to high school, you're going to be writing papers to write up, like big papers that you're going to write on your own. Because you're not there yet, I'm going to help guide you with how to write these papers and how to give your evidence through the lab investigation that you did. So in order to do that, you need to write complete sentences because eventually people aren't going to be able to read the question and your answer. You're going to be giving the information to them. If I went up to you and I said, it's going to decrease today, it's going to decrease today, what am I talking about?
The weather.
It could be about the weather. Okay, what else could it be? Water level, right? The time of school. Okay, did I make it very clear what I'm talking about? No, if I just said it is decreasing, you're like, what is Ms. Bishop talking about? Because you didn't say what it is. So you need to tell the reader, okay, that the temperature is going to decrease today. All right, you need to be very specific. So that's why we're going to make good, solid conclusion questions, basically rewriting the question in the form of a statement that gives all the information the reader is going to need without rereading the question. So let's look at number 1. The question is, what happened to the distance traveled by the spool racer as the number of rubber band winds increased? So it says hint, think of the hypothesis. If manipulated, then responding. So what manipulated is, it's the thing that we changed in the lab, the first thing before we measured. So by looking at my spool racer here, okay, as I increase the number of winds, okay, then what's going to happen? We're going to measure how far the spool racer travels. So that's going to be the manipulated variable. The manipulated variable is what we do first. Please underline the number of rubber band winds. And above that, I would like for you to write MV. Now, the manipulated independent variable is the same thing as independent variable. Science tends to use manipulated variable. Math tends to use independent variable. So I'm just going to write MV and IV on both. There. So just be aware, manipulated variable and independent variable mean the same thing. So then the dependent or responding variable is what we're going to measure at the end, hopefully quantitatively. What do we measure at the end after the spool racer travels? The distance. So please underline the distance traveled by the spool racer, and let's write RV equal or slash DV. Responding variable is the exact same thing as the dependent variable. Math tends to use the word dependent. Science uses independent, but since math and science are really good buddies, I'm just going to call them both. Gage, are you writing this down and highlighting this information for when you turn this in? All right, now let's make a statement. So we're going to talk about what we're going to do first. So I'm going to use that information that I had in the question and rewrite my sentence. So I'm going to say as, and write kind of small, as the number, should I just say as the number increased? Did we just say that was a good way to tell people information? No, you want to give details. As the number of rubber band winds And science loves words like increased, decreased, comma, because we're on the next part. Do I say as the number of rubber band winds increased, it went up?
The distance.
Yeah, specifics. The distance traveled. The distance traveled by the spool racer. Okay. And I know a lot of you guys are probably going to have a really good guess about what's going to happen, but it's really good idea not to take a guess until you have data to back that up. I know you guys are probably like, Miss Bishop, I know what's going to happen. You're probably right. But still, I'm going to leave this blank because I'm not going to write a statement until I can prove it. It's being a really good scientist. So this is how you write a good complete sentence. Your reader should be able to tell exactly what you're talking about without rereading the question. Because again, you're eventually going to write your own papers. And if you just tell a reader it's going up, that doesn't help the reader one bit. And you're probably not going to get a very good grade. All right, I'm going to do one more practice with you guys. So in this question, I basically used every single word because I want to be clear to the reader what I'm trying to say. So the question is, identify the part of the investigation when potential energy was observed. How can we write a statement using almost all those words? Can someone volunteer? How can we make a statement using almost every single word in that question? Instead of saying identify the part, we have identified it. Kian, what could we say?
Maybe in this investigation,
Oh, I like it.
I identified this type of potential energy.
Excellent. So he basically is using all the words he just saw. He talked about the investigation, he talked about the part, and he actually used the specific words potential energy. So I'm going to underline as much of that word as I can because that's what I need to rewrite. The part of the investigation in which potential energy was observed. And I'm going to make a line with the period behind it to remind myself to go back and fill that information in. You're going to get 5 points for complete sentences, 5 points for the answer. So make sure you remember to come back and answer those questions. You will get points off for saying the part of the investigation in which it is observed. We need to know what it is. All right, could everybody turn back to the instructions? That's on page 2. Again, I'm making a video right now, guys, of this. So if you need to rewatch anything, if you're a remote student, you can come back and watch that video after class. I'm going to put it on today's agenda. But for now, let's get to the fun part, build a spool racer. So when you get to your lab group today, you're going to go take a tray of supplies, and here's what's going to be at your desk. You're going to be working on the ground, not the lab tables, because eventually the spool racer is probably going to travel further than a lab table. Be very aware that you're not stepping on hands, fingers, or other people's supplies. Don't take your cell phone and put it on the ground or anything like that because you don't want someone to accidentally walk on it. So first thing, build a spool racer. Thread the rubber band through the main hole. So you've got a few different toothpicks here. They've probably already broken from previous classes. You'll see one that's got a nice black surrounding on the outside. That's to remind you guys not to break these. These are the nice sturdy toothpicks. You're going to point the rubber band, right? And you're going to have the rubber band on the other end, get it nice and centered. And you're going to push the rubber band as far as you can into the spool. Kind of hold the rubber band in place. It's okay if it doesn't go all the way in at first because you can use the other side to loop through. So you're kind of digging into the spool until you've got the rubber band out. Okay, so I've got a loop on each side of the spool racer. You're going to take one of the flat toothpicks, it's probably already broken, and you're going to break it or use a toothpick that does not go past the wheel. If it goes past the wheel, you might have some friction that's going to stop it. So I want to make sure that no piece of the toothpick is outside the length of the wheel. See mine here? You're going to take a small piece of tape. Same thing. Tape is sticky. It's going to cause friction if it's sticking out beyond the wheel. And you're going to tape that tape down. Do you guys see I'm not going past the wheel? We don't want anything piece on the side that's going to stop the spool racer from moving forward. Then next part, this is a washer, and it's has a really helpful job to help keep knots and loops from happening in the center of the spool. You're going to tape the washer, and you're going to pull it through the spool. Now, you're going to turn the loop so it's on the right side. We have a pencil, and these are actually kind of special pencils here. They're not sharpened. These pencils are not for you to use. I will give you a sharpened pencil. It is because we want all of our pencils to have the same mass for each one of our observations. So every lab group should have the same supplies. We should have close to the same data there. We're going to insert the pencil into the loop we made, and we want the pencil to be on the right-hand side, and we want the eraser to go forward. The eraser is going to be the front of our spool today. We want this part to be smaller in length than this part, because when I eventually put the spool eraser down, if this part is heavier, it's not going to go forward because the eraser is going to stop it from going forward. Do you guys see that? When I press down, it should go right back up because this part is going to be heavier than this part. This is going to be the front. Now we're going to take our spool eraser and put the eraser up towards the ceiling. We're going to take our finger, our right finger today, and we're going to do a loop. We're going to go forward. I want you guys to do it with me. Push forward. That's the direction we want the spool eraser to go. So up and down. So I'm going to do one up. That is one. You're going to use the tiles on the floor and the meter sticks to make kind of a marking start line. So this is a meter stick, not a yardstick, and you're going to want to start with 0. We're measuring in centimeters today, not meters. There's 100 centimeters in a meter stick. You might need 2 meter sticks today. So when I assign you guys to work, make sure you pick up 2. You're going to place the spool on the ground. Notice how I did not let the spool get tangled or anything. I put it directly on the ground behind the finish line, and I'm going to release. If it doesn't move forward, that's okay. There's not enough potential energy right now to make it move forward. So what would I write here? All right, I don't want you to write this down, guys. I'm just doing an example, okay? But just so you have an idea what to do. 0 centimeters. Okay, I'm going to pull my rope tight, my rubber band. Okay, I'm going to see that there's no loops still in the spool eraser. I'm going to try again. This time I'm going to do 1. Eraser's back up the ceiling. 2, 3. Okay, I've got 3. Now I'm going to put it behind the line. I haven't let the spool eraser turn at all because the rubber band's underneath. I'm going to release, and it's probably going to move forward the second time. You're going to take your measurement right here at the beginning of the wooden spool. Next time, I'm going to write down whatever it would be. Let's say 9 centimeters. You will get -1 point off on the slab if you don't write centimeters. Our numbers need to mean something. So next, let's say I do 5, put the spool eraser down. You're going to see it's eventually going to move quicker there. Eventually, there's going to be so much elastic energy that it's going to outweigh the friction on the floor. It might start to spin out when you go over to the 11, 13, 15 spins. Just try to move your meter stick around to measure the length that it traveled. It's okay if it doesn't go in a straight, perfect line. So after you're done with this part, the data table, you're ready to make your graph. Don't do the graph until you make your data table. The only thing I want you to do on your graph right now is to start labeling the x-axis line. The x-axis line is here. You're going to start with 0, and because I've made this lab, so I know exactly how many squares there need to be, we're going to write down the manipulated variable, which is the number of what? Lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, because that's how many winds I have asked you to wind your spool eraser today. Eventually, your group is going to make a y-axis. Now, don't start labeling 1, 2, 3, 4, 5, 6, 7 all the way to 13, because I'm telling you, your spool eraser is going to go past 13 centimeters. Later on with your group, you're going to have to decide, should we go up by 5s? Do we need to go up by 10s? Maybe some of y'all might even need to go up by 20. Got a nice new rubber band. You don't want to decide this number line until after you see the maximum number that the distance of the spool racer traveled here. These lines can't go up 1, 13, 62, 73. They need to be the same number throughout. And you want to try to use as much of the graph as possible. Like, don't go up by hundreds because your graph is going to eventually look like this. It's going to be way too hard to see. You want to use as much as possible. So I'm going to show you guys just an example with some made-up numbers, what it's going to look like. When you don't wind the spool racer up at all, how far is it going to travel? 0. So I'm going to do 0 centimeters. I'm going to go left and right first at 0 winds, 0 centimeters. I'm going to make a dot. Now let's say on 1 wind, which is right here, it didn't travel. I'm going to make a dot, and I'm making a line graph because I'm going a distance. The spool racer is not going to just jump from 5 centimeters to 20. It's going to travel and eventually stop at 20. So let's say on 3 winds, maybe it goes up, and I'm going up by, pretend I'm going up by 10s. It goes up 10. So I'm going to do 3 winds and up 10. Then on 5 winds, let's say it went up 40. I'm going to go up over 5 winds up to 40. Say it's 7. It jumps all the way up to here to 90. Eventually, your line graph is going to look like this. It should not be a perfect line unless you have a really, really good lucky spool. That's okay if it's not. Don't do the line graph until after you're done with the data itself. Does that make sense?
Yes.
All right. So first thing you guys need to do when you get to your lab is you need to build your spool racer. Reading comprehension, your graphing, conclusion questions can all happen at a later date. What can't happen at a later date